You know that scene in Terminator 2 with the T-1000? Like oozing through those metal bars, changing shape at will. Well, it turns out that sci-fi fantasy, it's becoming less fiction every day and more science. So today, we're taking a deep dive into these magnetic shape memory materials. MSMMs for short. And trust me, it's going to get really interesting. We're going to unpack how these materials work, like at the atomic level, and why they have the potential to revolutionize everything, from robotics to medicine.
It is amazing how quickly science is catching up to what we used to only imagine in movies, right?
Right.
These MSMMs, they can actually change shape in response to magnetic fields. And there are two main types we'll be exploring today: MSMAs, the alloys, and MSMPs, the polymers. And by the end of this deep dive, you'll understand the key differences between them and why they're both so exciting.
Okay, so let's start with these MSMAs. They're primarily made from something called Heisler alloys, right?
That's right.
But the thing that really blew my mind was that these Heisler alloys, they can be magnetic even when the individual elements aren't. What's going on there?
That is one of the things that makes Heisler alloys so fascinating. You can have nickel, manganese, and gallium, none of which are magnetic on their own. But you combine them in the right proportions. You get the right crystal structure. And they exhibit ferromagnetism. It's all about how the electrons interact within the alloy lattice.
So it's like the whole is greater than the sum of its parts.
Exactly.
That's pretty cool. But how does that magnetism actually translate into shape change? Are we talking about like tiny little gears inside these alloys?
Not gears, but
Yeah.
it does involve rearranging structures at a microscopic level. So picture this. Inside these alloys, you have these tiny regions called twin boundaries. Think of them like grout lines between tiles. But at the atomic scale, when you apply a magnetic field, these boundaries can shift, causing the entire lattice structure to rearrange itself.
So these tiny tiles, they're flipping and rearranging based on the magnetic field. And that somehow makes the whole material change shape.
Exactly. The rearrangement of those twin boundaries at the molecular level leads to a macroscopic shape change. It's like a domino effect, but on an incredibly small scale. And then there's another process that can also happen called martensitic transformation. This is where the alloy undergoes a phase change, transitioning between different crystal structures. Again, triggered by the magnetic field. It's kind of like how water can exist as ice, liquid, or vapor, depending on the temperature. But in this case, it's the magnetic field that drives the transformation.
So you've got these two different mechanisms happening at a microscopic level: the twin boundary motion and the martensitic transformation. And they're both contributing to this shape-shifting ability. And I'm really curious about the applications for all of this.
Well, one area where MSMAs are already making waves is in actuators. These are devices that convert energy into motion. And because MSMAs can react so quickly to magnetic fields, we can create super fast actuators, up to 100 times faster than conventional technologies.
Wow. I'm trying to imagine like a real-world example, how that speed could be harnessed. What's an area that could be like transformed by these MSMA actuators?
Well, think about camera lenses, for example. The autofocus mechanism relies on actuators to move the lens elements. Now imagine those actuators are powered by MSMAs. You could have a camera that can focus in a fraction of a second, capturing fleeting moments with incredible precision.
Wow, that would certainly change the game for photographers and videographers, but I understand there are also applications beyond just speed. What about this magnetocaloric effect? You mentioned that earlier. What does that have to do with MSMAs?
Oh, that's a really interesting aspect of these materials. When an MSMA undergoes a martensitic transformation due to a magnetic field, it also experiences a change in temperature. This is the magnetocaloric effect, and it has some really exciting implications for things like refrigeration. Imagine a refrigerator that uses magnets to cool things down. Instead of relying on harmful refrigerants, that can damage the ozone layer. MSMA-based refrigerators could be much more eco-friendly.
That's pretty remarkable. Are there any prototypes in development for these kinds of magnetic refrigerators?
Absolutely. It's still early in the development stage. But researchers are actively working on prototypes of magnetocaloric refrigerators. The technology holds immense promise for more sustainable and efficient cooling solutions.
So we could be looking at a future with eco-friendly fridges powered by magnets. That's pretty incredible. What other applications are scientists exploring with these MSMAs? What about tiny sensors?
That's another exciting area. Researchers are developing MSMA-based MEMS, or microelectromechanical systems, which can be used as incredibly sensitive sensors. They could detect tiny vibrations of machines and structures, which could lead to early warning systems for potential failures. Imagine bridges with MSMA sensors that alert us to structural weaknesses before they become catastrophic.
It's amazing to think how such tiny materials can have such a huge impact on our safety and sustainability. It sounds like MSMAs are poised to revolutionize a ton of industries. But I'm guessing there are some challenges too, right? No material is perfect.
You're absolutely right. One of the main challenges with MSMAs is their brittleness. They can be fragile, prone to cracking, which can limit their use in certain applications. Another issue is temperature. MSMAs lose their shape-shifting abilities above a certain temperature, known as the Curie temperature.
So kind of like Goldilocks, huh? Not too hot, not too cold. What about those MSMPs, the shape-shifting polymers? Do they offer any advantages over MSMAs in terms of these challenges?
Well, MSMPs have their own unique set of strengths and weaknesses. Let's unpack those next. So these MSMAs are clearly remarkable, but those limitations, in terms of brittleness and temperature sensitivity, they do raise some concerns. And that's where these MSMPs come in, the magnetic shape memory polymers.
Okay, I'm curious to learn how these MSMPs differ from the metallic MSMAs. Do they rely on those same microscopic mechanisms, like the twin boundaries and phase transformations?
MSMPs work on a completely different principle. Instead of relying on changes in the crystal structure like MSMAs, they leverage the power of embedded magnetic particles within a polymer matrix. Think of it like dispersing tiny iron filings throughout a flexible, rubbery material.
Okay, so it's not about the inherent structure of the material itself, but rather how these magnetic particles are arranged within it. That's a fascinating distinction. But how do you actually program these MSMPs to change shape?
It's actually a pretty ingenious process. You start by heating the MSMP, making it soft and malleable, and then you mold it into your desired shape. As it cools down, you maintain that shape under a bit of stress. This essentially locks the magnetic particles in a specific orientation within that polymer matrix.
So it's like setting a temporary shape for the material, almost like creating a mold.
Exactly. And now, here's where it gets really interesting. When you apply a magnetic field to that cooled polymer, those embedded magnetic particles, they heat up due to magnetic hysteresis. And that localized heating softens the polymer around it, releasing the stress. That was locking that shape in place. And as that stress is released, the polymer snaps back to its original pre-programmed shapes.
Oh, wow. It's almost like material with a built-in rewind button. That's a pretty remarkable level of control over shape change. I can see why there's so much excitement around these MSMPs. So what are some of the most promising applications being explored right now?
Well, one area that's generating a lot of buzz is biomedicine. Imagine a self-expanding stent made from an MSMP. It can be inserted into a blocked artery in a compact form. And then, using a targeted magnetic field, it would expand to open up the artery.
That would be a game changer for minimally invasive procedures, no more complex surgeries or long recovery times. Are there other potential applications in the medical field?
Absolutely. Think about sutures. That could dissolve on their own after a wound has healed. Or how about targeted drug delivery systems? You could encapsulate medication within an MSMP and then use magnetic fields to guide it to a specific location in the body, releasing the drug precisely where it's needed.
That level of precision in drug delivery could revolutionize the way we treat diseases, minimizing side effects and maximizing treatment efficacy. It's incredible to think about the possibilities. What about outside the medical field? Are MSMPs being explored for applications in other areas?
Oh, tons. One area that's particularly exciting is soft robotics. Traditional robots that are often rigid and clunky, but with MSMPs, you can create robots that are soft, flexible, and incredibly adaptable. Imagine a robot that can squeeze through tight spaces or navigate complex terrain by changing its shape on demand.
So these MSMPs could be the key to creating robots that are more like living organisms in their agility and adaptability.
Exactly. And because that shape change is controlled by magnetic fields, you have this high degree of precision and control over the robot's movements. It really opens up a whole new world of possibilities for robotic design and functionality.
It sounds like MSMPs have the potential to really blur the line between living organisms and machines. But like with any new technology, I imagine there are some challenges and limitations that researchers are still grappling with.
Of course, every material has its drawbacks. One of the key challenges with MSMPs is their sensitivity to external magnetic fields. If there are other magnetic fields present in the environment, it can interfere with their performance. You wouldn't want to use an MSMP-based device near an MRI machine, for example.
Right, that makes sense. So careful consideration of the environment, where these materials will be used, is crucial. What about their durability? How do MSMPs hold up under stress and repeated use?
Well, durability is another area that researchers are actively working on. Polymers, by their nature, can be susceptible to degradation, especially when exposed to heat. So finding ways to improve the heat resistance of MSMPs is essential for expanding their potential applications.
So it sounds like both MSMAs and MSMPs have their own unique sets of strengths and weaknesses. But it's clear that scientists are making incredible progress in overcoming those challenges. So what are some of the most exciting breakthroughs happening right now in the world of shape-shifting materials?
That's a great question. There are some truly remarkable advances taking place. One of the most promising areas of research is focused on making MSMAs tougher and less brittle. So they're experimenting with adding elements like boron or cobalt to the alloys, and these additions, they can act like microscopic reinforcements, preventing cracks from forming and spreading.
So it's like adding rebar to concrete, but on an atomic scale.
Exactly. That's a great analogy. And on the manufacturing side, new techniques like 3D printing are opening up exciting possibilities. Imagine being able to precisely control the microstructure of an MSMA during the printing process, tailoring its properties for specific applications.
3D printing shape-shifting materials. That sounds straight out of a science fiction novel. What about MSMPs? What kind of advancements are happening in that area?
One of the most fascinating areas of research there is multi-stimuli responsiveness. So imagine an MSMP that responds not only to magnetic fields, but also to changes in temperature or light. This could lead to materials that can adapt to their environment in even more complex ways.
So we're talking about materials that can morph into different shapes based on a combination of factors. That's next level shape-shifting. What would be like a real-world example of how that could be used?
Well, think about a drug delivery system. That releases medication only when it reaches a specific temperature within the body, ensuring that the drug is delivered precisely where and when it's needed. Or imagine a self-repairing material. That, when exposed to light, it triggers a shape change that closes up cracks or damages.
That's incredible. It sounds like we're on the verge of some truly revolutionary applications. And you mentioned nanoparticles earlier. How are those being incorporated into MSMMs?
Well, researchers are finding that by adding tiny magnetic nanoparticles to both MSMAs and MSMPs, they can actually enhance their performance and gain even finer control over their shape-shifting abilities. These nanoparticles, they act like tiny magnets within the material, amplifying its response to external magnetic fields.
So it's like adding turbochargers to these microscopic transformers. What does all of this mean for the future? Where are MSMMs headed?
Well, if you connect all these advancements to the bigger picture, we're talking about a potential revolution in various fields. Imagine a world with shape-shifting medical implants that adapt to the body's needs, or self-repairing materials that can fix damage on their own, and robots that can change their form to navigate any environment.
Okay, I think my mind is officially blown. We've covered a lot of ground today in this deep dive. What are some key takeaways you want our listener to walk away with?
Well, MSMMs represent a paradigm shift in material science. They're not just a scientific curiosity. They have the potential to fundamentally change the way we live and work and interact with the world around us. From robotics and medicine to aerospace and sustainable energy, the applications are truly limitless. And with researchers constantly pushing the boundaries of what's possible, the future of MSMMs is incredibly bright.
It's been an amazing journey, exploring the world of shape-shifting materials. It's clear that we're just scratching the surface of what's possible with MSMMs. Who knows what incredible innovations await us in the future? One thing's for sure, the line between science fiction and reality is becoming increasingly blurred. Thanks for joining us on this deep dive.